Uh, so yesterday we discussed that problem. We did some examples, and then we went on and introduced frequency response. We saw how important is to design system or to know how to analyze system in frequency domain. Also, we discussed uh, relationship between S domain that for us to move from frequency domain from S domain to frequency domain, we just need to substitute S with J omega. And we actually proved that. And we said that that is only possible. Sorry, we said that is only possible when we are dealing with a sinusoid signal, as in our input are sinusoidal. Mm, uh, is there a problem? I can see some guys are like talking. Hello? Guys, are you okay? Can you hear me?
Yeah, we can hear you. There's no problem.
Okay, thank you. So we and then we went on and defined several frequency response specification, and I promised you guys that today we will do some formulation and also look at correlation between frequency response and time response. So this is what we will do. So first we'll go on and formulate frequency response of a control system, and this will be a second order system. Remember when we were introduced control system, we said that second order we can actually just uh, deal with second order system because a higher order system can actually be modeled or broken down to several second order system. So it is wise that we deal with second order system, and if you have any higher order system, you can break it down to second order system. For our course 411, I think also with all the control system related courses in electrical undergraduate, we'll just do second order system. So we'll go on and do some correlation between the time response and frequency response. In this first item, actually we'll formulate those frequency response specification. That is peak resonance, frequency resonance, and bandwidth. And then we'll see how these are related with the time response specification that we did earlier during this course. And then we look at one problem, one or two. If we won't get time to do those problems, then I'll just post these examples as screenshots. Mm. After this, when we meet again, we'll do graphical representation of frequency response. Frequency response. So to start with a frequency response control system, remember that in S domain, we say that our transfer function for second order system is given by this. So here we have S squared plus 2, our damping ratio, and then natural frequency S, and then you remember this standard form second order. So for us to move from S domain to frequency domain, remember we said we just need to substitute s as that. So for steady state, for steady state, sinusoidal response or frequency response, we'll get this j omega. So when you simplify, you'll get something like this: omega n plus square. So if we let u to be omega over omega, uh, that of natural frequency, then we can end up with we'll end up with 1 minus u squared plus omega u. So for to get magnitude, just need to, using the complex algebra. So our magnitude will be given by this squared, real squared, imaginary squared, sorry, and then square root of that. So that is the magnitude of this system, second order system. And for the first, you take minus tan inverse this value, the imaginary part, divide by the real part. The imaginary part over the real part. Actually, this is minus here because uh, it's actually a reciprocal. It is 1 over this complex number, 1 over this complex number. So if this is positive, if it's just a normal number, as in it's not reciprocal, then this negative won't be here. So once we have these, then we can plot our our response, our response. So the way, I just want you to get the feel of it. So if say u is 0, let's do for u is 0, u1, and maybe when u goes to infinity. So if u is 0, here we have 1 squared, and this one will vanish. So we just have 1 over 1. So obviously our m, or our magnitude, is 1. And our phase, if u is 0, it means the whole of this goes to 0. So tan inverse of 0 is 90, but there is a negative, so this is minus 90. If u is 1, then this part will diminish, will vanish. So here we have 4 dumping delta square 1. Sorry?
Tan inverse of 0 is 0, not 90.
Tan inverse of 0 is, yeah,
0.
sorry, yeah, it's 0. Sorry. is 0. Tan inverse of 0. Yeah. Thank you. So this is 0. When it is 1, this will be 0. This real part, this part will be 0, and then here we'll have 4 delta squared. Square root of it is just 2 delta. So m here is just 1/2 delta. And if this is 1, then here it means this part will blow up. We'll have infinity, right? So tan inverse of infinity is what? Minus
minus 90 degrees.
Minus 90. Yes. So as this goes to infinity, it means this denominator will be a very big number. Then it means m will go to will tend to 0. And if this is big number, it's a very big number. Here actually you'll get phi, or the face, as minus 180. So if we try to sketch at 0, if this is u, at 0 we'll get 1, right? At 1 here, since this is a small number, delta is less than 1, then we're assuming it's less than 1 for most of control system, then we'll have something going up and then down. So these are the same characteristic curve we show last time. That is yesterday. So remember when we are plotting the time domain for this second order system, we are having something like this. So this is the response for time domain, and this is the response for frequency domain. Sawa. And for frequency domain, you need to show both the magnitude and the phase. So the phase, you can try and plot this. You'll get something like this. So this is just sketching. So you'll get something like that. So at 1 you have 90, and then there you have minus 180. Let me just add these guys. So now we are trying to get the resonant frequency, those specification. Hello? Remember our magnitude for us to get this resonant frequency, which is frequency at this point, where magnitude is maximum, then it means we need to differentiate, setting derivative, or differentiate the magnitude, and then set that derivative to 0 for us to get this value, which gives a maximum magnitude. So the way we do it, we take this magnitude and then differentiate with respect to u. After that, you set it to 0, and then from there we can be able to get this value, the resonant frequency, which gives a maximum magnitude. So when you take that is you should get So when you differentiate, I did this earlier, you get something like this. So for us to get this value at maximum of maximum m, maximum magnitude, we need to set the derivative to 0. So when you set this derivative to 0, it means this denominator will disappear, because this denominator will go and multiply 0. So we'll end up with 4 is equals to 0.
Yes.
Okay, so here what we can do, we can factor that, sorry, so that we have u squared. Here we'll have 1 plus 2 is equals to 0. So solving this quadratic, we'll have 2 equations. So u is equals to 0, or therefore, so since you are looking for the resonant frequency, we can actually denote this as r. Because once we set this to 0, then it means we are looking for that frequency where there is maximum magnitude. So rearranging that, but we know our u is actually w over n. So we'll have, this is the frequency where, we'll have our maximum m, which is mr, and we call that frequency resonant frequency. Since this is a square root, then it means if our delta, our damping ratio, just look at this, if our damping ratio is greater than 1, then it means this frequency will be what? Will be an imaginary, right? And we can't have imaginary frequency. So for this to be valid, it means 2d squared must be less than or equal to 1, which will translate to so this equation is valid when damping ratio is less than or equals to 0.707. Sawa. Guys, are we okay up to there?
Yes.
Okay. And how can we get this? How can we get this MR, maximum magnitude? How can we get this? We can get this by substituting the value we got here. So this value here will actually give, or this value will actually give the maximum magnitude according to what we have formulated here. So if we substitute this into the magnitude equation here, we should get MR, the max. How come is this? Hello? Can you see this, guys?
Yes, which part?
Hello?
Hello? We can see. But which part are you talking?
No, I'm saying about this running out of time for the Zoom.
Yes.
Why yesterday or today I use different account? Okay. If we are logged out, then we'll join through our normal Google Meet, right? Please, yeah.
Okay.
Okay. So it means if sorry.
You can check if you can upgrade the meeting. It has been giving us notifications of meeting being upgraded.
Where? I don't know. I think today I used my personal. No. Okay. If we are logged out, then we just go through. We'll please join through Google Meet with today's link. So it should work. So our if we substitute this value which we got here to magnitude equation, then we should get our MR, which is the maximum maximum peak. So we can say substitute UR into what magnitude equation and simplify to get MR. So our MR will be 2 delta 1 minus delta squared square root of it. And remember, this is valid. This is valid for damping ratio less than or equals to 0.707. So what we can see from this, is that MR depends on what? Depends on NR depends on what? Damping ratio only. Damping ratio only. So MR depends on damping ratio only. And what about this? Resonant frequency. Resonant frequency depends on two items. That is damping ratio and natural frequency. Sawa. Guys. Okay.
Yes.
So we have two specification. One, resonant frequency, this peak. So what is remaining is the bandwidth. And remember, bandwidth, we say this is the magnitude where the value drops to 70.7%. So the only way the way we get to this bandwidth is when we set our magnitude. We set our magnitude to what? Set magnitude to this approximate, which is 0.707. So approximately to that. So if you have our magnitude here, this equation, so you take this equation, you equate to 1 over root 2, 1 over root 2, and then you simplify. So you have 1 minus u squared, that square root, and then you have 2 delta u squared square root is equals to 1 over root 2. So you can square on both sides. So if you square on both sides, or you cross multiplication, so you'll have something like 1 u squared half plus 2 delta, like that. So if you square and rearrange, you should get something like this. So this u is the one which will give you bandwidth. So solving for u using quadratic, so you can use your quadratic equation. Just give me 1 minute. So sorry about that. So once you solve that, you'll have ub given by that, and we know that u is, so for our ub so this is the whole of that into here. Sasa. Hello? We have all the specifications. We have omega r, mr, and the bandwidth. So make sure you know how to derive this. What we want to see next, is that for a given damping ratio, the bandwidth is actually a measure of what? A measure of natural frequency, this natural frequency, and hence the speed of response. So it means if the bandwidth is more, So it means if the bandwidth is more, if the bandwidth is more or is large, the speed of response is high. This is because of this settling time.